welcome. So I'm going to, hello again, everyone. Thanks a lot for connecting. And I'm going to continue with the lecture that I was giving yesterday, which was about rare decays of heavy hadrons, if you remember. And okay, hopefully I will have some time to talk about mixing and CP violation, if we have time. If not, it will be okay, because Karim Travelsi will talk a lot about it, I guess. So if you remember, we were explaining that it is what we are looking for. It is a very rare decays with branching ratios which are very small, and they are very difficult to measure. I was explaining how to measure. There are different ways you can measure absolute branching fractions, or you can measure relative branching fractions. At the end, what you are doing, it is to reconstruct the event and then to count how many events I have in my mass distributions, for instance, okay, or some other observables that we are going to talk. This is from the experimental point of view, and from the theoretical point of view, you have been hearing about how, if you remind the Fermi's theory of the VDK, how you can, the propagator here, and you can replace it like just by a constant, the Fermi constants. So in the case of rare decays, we can do something similar. And what we are going to do, it is that for the Flavour changing neutral current processes, all the effect of the loop, we are going to have it in effective vertices. This is what it is, the operator product expansion. I'm sure that you have been hearing a lot during these lectures, or if not, you will hear more for sure from Professor Virto. And as I told you, the idea it is that at the end, the amplitude of a process, it is given by the CKM matrix elements that we were talking already. These Wilson coefficients, which are replacing all these effects here, so in kind of a effective vertex, and then we have also the hadronic matrix elements, okay, which are computed by lattice QCD. So you have different operators depending on the process that we are involved, and then you have different coefficients. So then you have for instance, the photon operator, you have the leptonic operator, the quark operator. So then they have different numbers, and then you have a coefficient which is related. Each of the number of the coefficient, it is related to the kind of process that you have in the loop. Okay. The idea it is that, okay, these coefficients, they can be calculated in the standard model with high precision. And if you have a new particle, if there is something in these loops, in these vertices, that will mean that you have a contribution of the Wilson coefficient coming from new physics. Okay. So the idea it is that, okay, you calculate, the theory calculate the coefficients, the experimental try to measure and to check if these are consistent with these coefficients. Okay, if we are at the electroweak scale, we will have a contribution of the W. If there is new physics, then we have it will become in the mass of the new physics. Okay, it will be related to the mass of the new physics. In addition, because
so, Arantza, there's a question from Juhi in the chat about whether they're Q-square or scale dependent.
You will see it in the next slides.
Okay.
Okay, you will see this depend. You have different, depending on the Q-square, you have different ratios of different contribution of the Wilson coefficient. We can talk if not later. Okay, and so sorry. So then, what I wanted to say. So the thing is that because in the standard model, the right-handed currents are suppressed. You have just the C prime coefficients are supposed to be 0, so you should not have any C prime coefficients. You will see, which are related to the right-handed, and you can check if you get something, if you experimentally find something related to this C prime coefficient, that will mean that you have some right-handed currents which are not predicted by the standard model. Okay. So one example it is, for instance, the decay width for the VS2 the width for the VS2 mu mu decay channel. You can express it from the theoretical point of view. So you have the Fermi constant, you have the kinematic factors, you have the mass of the VS, you have a decay constant, which is FBS, the CKM matrix elements, as I told you. And then here in this process, you are sensitive to this C10 coefficient, which is related to the O10 operator. Okay, so then one can express each of the observables, each of the branching ratios of the different rare decays, you can express it in terms of these Wilson coefficients. Okay, so because each operator, because you have sensitivity to the different operators, so depending on the process that you are considering, you will be able to check one coefficient or another one. Okay, for instance, in the case of the radiative processes, B2X gamma or B2 castar gamma, what you are going to check it is the C7 or the C7 prime coefficient, Wilson coefficient. In the case that you have a semi-leptonic decay, you are sensitive to all of them. I will explain. And in the case of the BS to mu, as I have showed you the expression, you are sensitive to the C10. Okay. So about the rare decays, the first measurement of a radiative decay was by Clio2 at the epsilon-4s. The B2 castar gamma, it is the radiative, so branching ratio is of the order of 10 to the minus 5, as I explained yesterday. And here you can see this is the event, is how it was reconstructed. You can see how few events they have in different channels. Just using 1.5 millions of BB events, as we got about tenths of events. Okay, the branching ratio was measured, and it was really a very interesting thing because it was able to check the standard model. Okay, predictions. Something that I think Karim also will explain more clear. The variables that you use in at B factories, or this was done at Clio, so you have the different the different distributions that it was obtained in this analysis for the castar gamma, and it is the variables that they are usually at the epsilon-4s, and I'm sure that you know if you are working on Belle. It is this delta E variable, which is just it is related to the beam energy. It has to be about 0. Okay, so then you have it here, and the mass constraint variable, which is also related to the beam. You know the energy of the beam, and then you know the castar and the photon momentum, and then you are expecting that this is picking around the beam mass. Okay, apart of course from the mass of the castar, which is decaying into a cation. Okay, so this is the kind of variables that it is usually used in the B factories. I'm sure that Karim will talk more about it. But just for you to know it, that even more suppressed than the B2 castar gamma decay that it was obtained by Clio, Belle was able to measure the B2D gamma decay. Okay, this is much more suppressed because it is this transition B2D, and with 657 millions of dimensions, this is the number of events that you get in these different decay channels. So B2 rho gamma and B2 W gamma. Okay, you can see these are the branching ratios, and these are the variables that I was talking. So you have the delta E energy, and the branching ratio it is about 10 to the minus 7. Okay, so another decay, another rare decay, even more rare, it is the leptonic decays BS to mu mu. Maybe you have heard about it. It is a very important decay. It is very rare. It is, in addition to be flavor changing not occurring, it is LHC suppressed, and the branching ratio of the standard model is 10 to the minus 9. Okay, it has been searched for over the last 30 years. You can see from many experiments, and you can see the sensitivity at the time, and in the 80s it was 10 to the minus 4, and it has been evolved with the experiments and with the statistics that we have. And finally, in 2012, the CMS experiment and the LHC experiment, they detect this decay, BS to mu mu decay channel. The B to mu mu channel, it is still not observed yet, even if it is predicted by the standard model. So this is a complicated event. You can see here in the LHC experiment, you are expected to have 2 muons in the final state, but you have a lot of tracks, and it is very difficult to disentangle from this. It is so difficult because you have a background. So there are many, many events which have two muons in the final state. So the background rate is expected to be of the order 10 to the -1 as compared to the signal. And that means that, okay, you have to be very good in the reconstruction, and then you have to be, you remember, very good impact parameter resolution. You have to be able to distinguish the muons that they are coming from this B, from the signal, or from any other B that they come, for instance, come from semi-leptonic decays or from any other much more abundant processes. And even like that, it is even more complicated because you have many, many processes. You have many resonances, for instance, that they are decaying directly to two muons, and they are three-level processes, or they are just hadronic processes. And then you have a lot of resonances decaying to two muons, a lot of two muons in general, which are not coming from your signal. So then you have to have a very good trigger, and then you have to be able to distinguish. And but yeah, it was very good that we were able to do it. We were able to reconstruct these events, and we had the first evidence in 2012 by LHC and CMS, and you can see clearly the peak. This is for the BS. This is for the BB. The BB was not observed because you don't have enough resolution, but the B and enough significance. But for the BS, the fit was given. And I advise to read this paper, which is really a very nice paper about this decay mode, the BS to mu. And the branching ratio that it was measured, it imposed very important constraints in new physics models, because there were many Sugra models or Susi models that they were predicting a branching ratios, which were much more higher as compared to what it was expected by the standard model, what it is computed by the standard model. And then all these models were eliminated by this channel, by the measurement of these channels. There are new results now from LHC with all the statistics. You can have it here. And you see now the very clear peak is there. Unfortunately, the VD decay into two muons is still non-significant. We have just put a limit. So this is, and then when you compare to the standard model, this is the standard model, and this is the result that we get. Okay, so it seems that it is in agreement with it. This decay has also been measured. The BS to mu has also been measured by Atlas CMS and LHCb. I don't know if you can see here. If you combine all the measurements, this is the significant. I mean, the difference with the standard model at 1 sigma, 2 sigmas, and 3 sigmas. So the standard model is here, and this is the result of the combination. Okay, so it is still below but compatible with the standard model at 2.1 sigma. Okay, and in the case. Okay, you can see here is the same. This is the same information. Okay. Then even more rare, it is this B to mu that it is still, we are still there. So we don't know if, I hope that we will find it very soon. And at present is we have just a limit that it has to be less than about 2 times 10 to the minus 10. Okay, and the prediction of the standard model, it is just there. We are around here. So other important decays and very, very interesting, it is the case of the B mesons, which are decaying in addition to leptons, also to anhydron. This is the semi-leptonic, what we call rare semi-leptonic decays. Okay, this is the kind of process. And here, this is where you have the dependence on Q square, because you have these two leptons and the final state. You remember it is just the form momentum transfer between the initial and the final stage, or this sum of momentums. And if you are studying the differential decay width as function of this Q squared, then what you see it is that you have different contributions depending on the Q square region that you are. So then you have in the very low Q square region, you are sensitive to this C7 or C7 prime coefficient, because you have the photon here. If you are in this region in the middle, the Q square region like that, then you are sensitive to C7 and C9. And at the end of them, with a high Q squared, you are sensitive to C9 and C10 coefficients. These two peaks that you see here, these correspond to the charmonium resonances. So then you remember the Jeb size that we were talking. So then this process, they are not rare, and they have to be suppressed. So usually you are going to see in all the analysis, in all the results that I'm presenting and that you will see in the future also, you will see that this region of Q squared, they are B to it. They are not, we are not looking at this region because you are completely dominated by these decays, okay? And the standard model values are computed, and they are well known, okay, as I told you. So let me explain a bit about this. How do we measure this? And for instance, suppose that you use one decay. This is in the case of the VS decaying to a phi and to muons. So the phi meson decays to a 2 counts. So what we can do it is to reconstruct the mass of the 2 counts coming from the phi and the 2 muons, and then you will see here, this is the mass of the KK mu mu, and then you can observe here that you have a more population of the events here, which if you project it, you will see very clear the peak of the mass of the VS. Okay, this is when if we plot the mass of the VS decay products as function of the Q square, and in the case of if you are projecting in this direction, in the y-axis, you can see the Q square, and then you can see this is the different regions where you have the very clear the Jeb psi and the psi 2s, okay, resonances. And then what it is important, it is that there you can do it is to define which are the regions that you are more sensitive and you are not affected by the background. Okay, so this is what usually this kind of plots you will see also very often, just the Q square dependence on the mass, the mass versus the Q square. Okay, so if we quote, or if we measure this differential decay width as function of Q square, what it has been observed, it is that we observe that if we compare with the theory, which is coming from lattice and Lytham-Son rules, we observe that there is a deviation as compared, a local deviation as compared to what it is predicted. And this is in the case of the VS25 mu mu channel, that it is 3 sigma away from the standard model prediction. But this has been tested with many other channels, and we observe quite a significant deviation in each of these modes. So then you have for the B2K mu mu, for the VS25 mu mu, for the B2 Castor mu mu, and also for the lambda B2 lambda mu mu. Sometimes it is not too much significant, but sometimes it is. And in general, we observe that we have a smaller branch inflections than the standard model prediction. You see, this is just the Q square distribution. So it is the differential decay width as function of Q square, where you have this Jeb psi and psi 2s resonances B to it. Okay. So in this region here, we are sensitive to the C9 and C7 coefficients, as I told you. This is when we measure this the differential decay, the differential branching ratio as function of Q square. And here in this kind of first observables, we are affected by lattice, by hadronic effects, okay, by QCD. And the theory is not so well precise. But we can do measurements in other observables. For instance, what it is just the angular distribution, which can be well measured. And we have done that. In this case, it is complicated because, you have different angles. It is similar to what I was explaining for BCB. So you have different functions which are depending on these Wilson coefficients also here, okay, in all these. I'm not going to go in detail, but you have, for instance, the lepton angle or the Cowan angle, so that they have a different angular distributions, and you can measure these distributions, the angular distributions, and then related to these Wilson coefficients. Okay, And this is what we observe. So this is for the different of these observables related to the Wilson coefficients. In general, for this channel, for the BS25 mu mu, we observe a good agreement with deviations that they are less than 2 sigma. But this we have done it with many channels. We have measured with a lot of channels, and also using what it is called optimized observables, which are ratios of the functions which are in this differential decay width, dependent on the angles. So if we use some ratios, some specific ratios, then they allow to cancel the contribution of form factors, and they are cleaner as compared to other observables. Okay, and this has,
sorry, Arantza, another question in the chat. Asking about the sources of uncertainty on the branching fractions for these rare decay. Yeah.
In the branching ratio here, the main sort of, so the main source of uncertainty, it is, I think it is from the theoretical point of view, as you can see from the bands, I think in this region it is lattice, it is Line-Thompson rules, and in this region it is lattice. From the experimental point of view, I'm not so sure. Probably it is also coming from the background substantiation or some efficiencies. I should check it. But so the main difference, the main error is coming from theory at present. In this is all QCD effects.
Thank you.
You were saying about measurement, right? Measurement, yeah, I'm not sure. I have to check which is the main source.
Okay. Thank you.
And yeah, so then there is there are quite recent analysis also from LHC, and then you can see this is when you compare with what it is expecting from the standard model for these coefficients, we observe that we have deviation about 3.4, 3.1, and 1.9 for each of these different decay modes. Okay, so it looks like there is a negative shift for one of the Wilson coefficients related to the muons, which is preferred over the standard model hypothesis at the level of 2-3 sigma. Okay. So even like that, as I told you, this kind of observables still are affected by the theoretical uncertainties coming from QCD. So there are other kind of observables which are cleaner, which are the ratios of this kind of decay mode, which are also testing the lepton universality. I think you will have dedicated lectures on that, but just let me to show you briefly. So what we can do is to measure the branching ratio of, for instance, these semi-leptonic and rare semi-leptonic decays into muons and into electrons, and then because the standard model the leptons are expecting to behave in the same way, you will have something like 1 plus minus some correction factor. Okay, and the theory it is quite precise because you have this hadronic form factor cancellation, and the main issue it is that because the electrons are radiating, they have radiation, you have Bremsstrahlung, you have to recover all this radiation to reconstruct the events. Okay, this is the at LHC at least. And experimentally, what we do it is to at LHC to avoid or to cancel systematic uncertainties. It is to refer to some specific channel, for instance, the YEPSI, which is the case also into muons or to electrons, and then like that, what we do it is a double ratio, and then we cancel many of the uncertainties at the experimental level. So you see the difference when we are reconstructing. There was a question also related, okay, what it is better to reconstruct muons or to reconstruct electrons? This depends on the experiment, and you can see, for instance, in LHC how much better it is to reconstruct muons as compared to reconstruct electrons. In our case, electron it is much more complicated. You have much more background. So this is just the mass distributions in the case of the P to K lepton when you are using leptons or when you are using electrons. And each of them, it is giving signals in the different detectors. So you have, for the case of the muons, you will have signals in the muon chambers. In the case of the electrons, you will have signals in the calorimeter, in the electromagnetic calorimeter. Okay.
So there's a question from Anshika in the chat about the double ratio. How could you just describe a little bit about why this is experimentally advantageous?
Yes, because you remember what I was telling. I don't know if you remember, but I was talking about that when you are measuring the branching ratio, you need to know the efficiencies of your detectors, the different efficiencies of the reconstruction. I don't know if you remember here. Wait a moment. Yes. Okay. When you want to measure the branching ratio, you need this selection efficiency, which depends on many things. Like, for instance, the trigger, that depends the reconstruction, the event reconstruction, what you are applying for the background subtraction, all these kind of things. For instance, the how well you are detecting your particles or whatever you are reconstructing. Okay, so if you are if you are using two different channels, which are which first one, it is well known, and like it is in the case of the YEPSI, which you know very well, this channel, you have large statistics, and it is decaying to the same final state as compared to your signal channel, then you, for instance, are able to cancel the efficiencies that they are coming. So, for instance, for the case of the muons, if I am taking the efficiencies to reconstruct a muon, because this is also, it has this term of the efficiency to reconstruct a muon, then it will cancel to some extent, not completely, but to some extent. You understand? It's okay. I don't know if I was clear enough. Let's hope.
Okay.
So,
yeah, yes.
It's okay.
Actually, now we've stopped you. I just had a question, actually, out of interest. With the electron channel, if one didn't do the Bremsstrahlung recovery, is how bad does it become in terms of the resolution?
Here, quite well. I cannot quantify it, but it is really, really bad. I mean, your signal, I think you cannot distinguish from the background. The electron, the Bremsstrahlung recovery, it is really important, and it has been very well checked with other analyses. For instance, the transverse asymmetries for the big 2 star EE, I think. So it has been very well tested.
Yeah, it's just a plot I don't think I've ever seen without the Brem recovery, just to see what it looks like.
I have seen it. I cannot tell you how much it is, but I think it is really, really bad. You have depending. I mean, it depends also. The resolution depends on the number of course, of the number of photons that you have. So if you are losing, if you have to recover more than one photon, it will be more high. But I cannot able to give you the number, but I can check it for sure. It is very important. It is very important. So you can see here, this is the difference, for instance, reconstructing the muons and reconstructing the electrons. So you can see how much it is the dilution, or how much you have this background. You can see here, you can see very clear the mass. When you project, you can see very clear the mass of the B. Okay, and here it is much more diffuse. It's much more complicated. You have much more background. Okay, in this all relation. Okay, so the most important thing is about this analysis is that if you do this ratio, what it has been observed, it was observed just with 3 inverse femtobarn at the very beginning with our Run-2, and now it has been measured by LHC with all the fuel statistic. And what we observe it is that we have a deviation from the standard model in this ratio, which is 3.1 sigma from the standard model. And this is and evidence of lepton flavor universality violation. Okay, the Barber and Belle experiments, they did the measurement also, but the statistic, of course, because it is a rare decay, it was much smaller, so it is compatible with everything. Okay, so this is quite intriguing, and what we have done also it is to measure in other channels, because and also one important thing, in the region that we are measuring, it is just this region, because if you look at the Q-square distribution, we don't want to have these resonances. Okay, so then we are there, we are in this region here to do the measurement. Okay, but we also have checked it not only with the B2K mu channel, but we have also tested with the B2 castor mu channel. So it is different hadronic final state, and this is the result with 3 inverse femtobarn, and this is the standard model predictions you can see here, and this is the results from LHC now into different bins of Q-square. Okay. Also, we have measured with lambda b to pk mu, and okay, this we don't have too much statistics, and then okay, it is below but still compatible. But you see, all of them, they have a decreasement as compared to what it is expected from the theory. Let me to talk about rare decays that they are radiative, that you have a photon in the final state, because there has been also measurement of this kind of decays. And this is very interesting, because the thing is that in the standard model, the photons which are coming in this kind of transition from B to S gamma, they have to be left-handed. So if you find a right-handed component in the process, when looking for this photon, then you could have signs of new physics in the loop. Okay. One of the analyses that we have performed is to study the lambda B baryon decaying into a lambda and a photon. This is quite sensitive, quite interesting because of the spin of the lambda B. And what we do it is to measure the angular distribution, just the LHC angle of the proton. And with this measuring this angle, you are sensitive to the photon polarization you are sensitive to the photon polarization contribution, because this parameter, this alpha gamma parameter, it is kind of giving you the left and right-handed contributions. Okay, and this we have done it very recently in LHC, and the result it is in agreement with the standard model, and this is sensitive to the C7 coefficient, so one of the Wilson coefficients. In fact, for the Wilson's coefficients C7 and C7 prime, the new physics contributions are not there. The different observables that they have been measured by different experiments, at present, they are in agreement with the standard model. So what we are observing, it is that the main contributions, the main differences with the standard model, they are coming from muons in semi-leptonic decays. Okay. But you can put all this information of the different observables. That means more than 100 observables from the different experiments, Belle, LHC, CMS, Atlas, all the experiments that we have, and then they are doing measurements on that. If we put all together, many theoretical groups, they have been working on that and doing global fits, and everyone is observing that the new physics hypothesis is preferred over the standard model by more than 4 or 5 sigma deviations. So the main effect is coming in this C9 coefficient, which is equivalent to muons, which it is preferred to have a contribution about -1 as compared, you can see here, as compared to what it is expected by the standard model. Okay, this is just the difference that you expect the new physics contributions, but it will be nice. And this has triggered many models with zeta primes, leptoquarks, new fermions and scalars. You can have many of these things that they have not been discovered. They have been also searched at the direct experiments, but they have not seen. But there could have something like that. So just a reminder that all what it has been predicted in an indirect, or it has been we have had signs in the indirect way, and that all the direct particles that they have been discovered, they have been about 10 years in advance as compared to what it was predicted. Okay, so what will be the next? Maybe we have a seed prime that it will be discovered in 10 years from now. Who knows? So, but what we are for sure it is having some kind of effects in BDKs, which probably in rare BDKs, which probably it is pointing, if it is confirmed, that we hope so, pointing some new physics and some new physics particles in the coming years. And that's all from this part that I wanted to explain. I don't know if you have questions. Or comments? If not, let me just to change subject a bit. No questions? No comments?
Nothing in the chat. So.
Okay, so I hope that you are still there. Okay, so let me just to finish this these lectures about talking about mixing and CP violation, and yeah, and I think that's all what I wanted to tell. I think this in any case this subject it will be very well addressed by Karim Travelsi, because it has been very important subject for the B factories, for the plus and minus experiments. But let me just to give you just a brief introduction that you will, I think it will be developed in the coming days for you. Okay, I think you have studied probably, Jim. That's right. They know about neutral mesons, about counts, the count systems. They are studying that in the.
Yeah. So.
Okay. Very good.
Yuval
so they know.
gave a nice introductory.
Okay, perfect. That's perfect.
both phenomena in his lectures.
Okay, perfect. Okay, so then I'm not going to give too many details, but just to remind you that these neutral mesons oscillate between particles and antiparticles. In the standard model, they can do it thanks to the electroweak force. Then you have this kind of box diagrams. And this is happening for counts, it is happening for charm, and it's also for the B system. And this was observed already in the 60s when I think you know about it, you have already heard about that you have the K shorts and the K long, which were decaying to 2 pions and 3 pions, and that it was observed at the time. It is that you have a regeneration. You were not expecting to have any K short at some time because the lifetime was very short, and then you observe that you have a regeneration of this K short, which were interfering with pions which were coming from the K long decay. Okay, this was observed there, and it has been very well already measured in this CPLR experiment at SUN. And we know very well how it is this phenomenology for the oscillations of kaons and in general. And I think then you have been explained, which is the probability that you have for oscillation for a neutral kaon to keep being this K0 or to be a K bar. Okay, you know also that you have been told about it, that at the end what you have it is that the K short and the K long, it is a combination of this K0 and anti-K0. Okay, so then you have the mass eigenstates are not the same of the Flavour eigenstates. And then you have the probability of the KS0 to keep it in that way or to oscillate. It is given by these equations here. This is the time evolution that you can see. And this depends on the mass difference of the two states, of the K long and the K short, and depends on the width of each of these states. Okay, and this has been studied, and it has been very well tested for the kaon system, and it has been also seen and studied for the observed by the for the charm system for the D0 meson, which has a very slow mixing as compared. You have the oscillation also for the oscillation pattern for the B0 meson, which is on here, or for the BS meson, which is in fact very, very fast. This is just the probability that you have to oscillate as function of the proper time. Okay. The mixing of the neutral in the case of the B meson, or this is in fact by general formulas, but okay, this is just for B's because it is there. It is governed by this equation. I think you know as the Schrödinger equation, and then you have this mixing that it is what it is that you have the light and heavy meson can be expressed in terms of the V0 and anti-V0 states. And then you have the P and Q here represent the amount of state missing that you have. Okay, this is some of the formulas that I don't know if you have seen already or if you are familiar with them. But one of the important things at the end in these formulas is that the mass difference, which is giving you the oscillation frequency, that is just the heavy, the mass, the difference between the heavy and the light mesons, and the bit difference. Okay, and you can see here this is in the case of the B meson system, and in the case of the BS meson system, how they determine the oscillation. Okay, in the case of the B system, you have a delta M, which is about 0.5 inverse picosecond, and the delta gamma, it is very, very, the width difference, it is very small, it is almost 0. And in the case of the BS system, you have a delta MS, which is 17 inverse picosecond, and that it is a delta gamma that it is about 10%. Okay. So this is the equations, the width that you have for the time dependence of the decay rate for initially pure flavor states. I suppose that you also have heard about it. I'm not going to give in detail of that. You have the different, these are the typical variables that we are measuring. And yeah, just to know it, this is the kind of equation with all the different terms that you have here. Okay. So the B oscillations, sorry.
Arantza, there's a question about the D system and why the mixing is so slow.
It is because this is the properties of the mixing of the charm. I have nothing about charm here, but this depends exactly on that. This is of the properties of the oscillations.
Yeah, I think Yuval talked about this yesterday, and you're right that it's to do with the strange quark being actually lighter than the charm quark, unlike the other cases where you have charm heavier than strange and top heavier than beauty. So these different properties. So I think if you look back at Yuval's notes, Anshika, that should give you a sense of why it's the case.
I have not the properties there, but yeah, it is just because that I don't have anything about charm here, unfortunately. So it's a pity. It was the charming thing was observed first time by Babar and Bell, and it has been confirmed by LHC with more than 5 sigma. But now I cannot remember exactly the values for the delta M and delta gamma. Sorry. So, but it is like that. So for the B systems, the first observation of B oscillation was by Argus in 87 at DESI. So they had about 5 events that they were oscillating from 20 that they were not oscillating, and this was the first observation. It has been very well precise measured by the B factories, Bell and Babar, the B oscillation frequency. And the VS, in the VS system, it was also in 2006, so it is not too far away. In 2006 was observed by CTF, so it was there was a clear sign of that there has to be an oscillation, and it has been confirmed and very well measured by LHC and other experiments now. Let me to explain you a bit how we measure this oscillation frequency for the different systems. So the formulas that you have when you have so the number of events that you are expected that they are not mixing, that they are not changing flavor and not flavor, that they are not becoming antiparticle, as compared to the ones that they are missing. It is shown here. So this is the dependence that you have with the oscillation frequencies, the delta M. And when you do just the asymmetry, what it is called the mixing asymmetry between these two equations, you have this that it is just sensitive to the cosine of the delta M times T. Okay, so then if we want to measure this asymmetry and then to extract the oscillation frequency, what we have to do it is to know well what did we have when it was produced, if we had a B0 or an anti-B0, and then what happened when it decayed, if it was a B0 or an anti-B0. We have to know very well which kind of particle or antiparticles we had it at the initial and the decay state. And then we have to know also what it is, because we need to have the time, what is the time difference between the production and then the decay. And this is, for that, it is very important that the experiments have to have a very good time resolution. And in the case of the Belle II or the B factories, this is really very good. It is just 15 femtoseconds, I think. And you have also for LHC B as compared to Atlas and CMS, it is also much better. Then this is just in the case that you have, this is in the theoretical, from the theoretical point of view. If you are including experimental effects, then what you have it is, you remember that we were talking about something that it is called mistag, which was telling that, okay, maybe we are wrong, and then we are thinking that we have a B0, but we have an anti-B0. This is giving the probability of that I am tagging my initial flavor when it is produced or decaying. And then also what I have for sure, it is also the resolution of the time, okay, the time resolution. So my oscillation, if I'm doing this asymmetry, okay, this mixing asymmetry, I will observe something like that, where you have the period, it is directly related to delta M, and I can measure it from that. And then, okay, I have some experimental effects that they are coming from these mistag effects, or if some of the events that I am not being able to detect. Well, okay, but in any case, it can be very well seen, this asymmetry, and to be very measured. Just remind you that I was explaining that, okay, the effect that you have at the end with this mistag or the resolution, it is of the time resolution, it is affecting quite a lot the oscillation. So you have a B meson which is oscillating between particle and antiparticle, and you have a big oscillation, and then if you are applying the different contributions from the different experimental effects, you will, at the end, you will see that it is not so high. This is in the case of the LHC B, and this is just for the BS system, just in some kind of simulation. But it is just to illustrate how it is affecting the different contributions of the detector effects. Okay. So we have performed for the BS system, we have performed this measurement of the asymmetry using BS to DS by events, so to checking which are the ones that they are oscillating and which are the ones that they are not oscillating. And here you can see a very, very well precise result of the delta M, the oscillating of the frequency for the BS system. So you can see which is the asymmetry shown here. Okay. What it is an important thing here, it is that so if you are able to measure this delta M, this frequency, what you can do it is to relate it to the CKM matrix element. You have this dependence here of this type, and then you can also have a constraint in the, you remember the eta prime and rho prime plane for the CKM matrix unitary triangle, and then to check if it is in agreement or if it is not agreement with the other measurements. This is giving this BTB over BTS constraint, and then you have it here in this circle here. So this is with the combined result from each FLAV, from the heavy flavor averaging group. You have combining all the measurements from different experiments. This is the results that there is. So you can see that it is very precise now, that the results now are very precise, and they are agreeing very well with the other measurements of the different observables. Okay. So I don't know if I have time, and I don't think that I will have too much time to explain the CP violation, but just explain you a bit that, okay, we will have a CP violation if we observe that the decay width that we have, the width that we have for one decay and so the decay of a particle and the decay of a antiparticle, it is different. So if the widths are different, okay, and there are three different types of CP violation. You can have CP violation in the decay, so that means that, okay, the amount of V0 going to a final state, it is different to the amount of anti-V0 going to the anti-final state. So this would just will imply that you have a direct CP violation, and this will mean that this is different to 1. The amplitude of these two processes is different to 1. We can have also violation of CP in the case that, okay, I observe that the amount of V0 that they are becoming to an anti-V0, they are different to an anti-V0 going to a V0, that it is a CP violation in mixing. And okay, this is governed by this equation here. Or I can have a CP violation in interference between mixing and decay. Okay, and this is studied usually using this CP asymmetry, which is okay, it is shown here. And then it is just this, you can do it because you can have a state which is decaying to a final state, and that it is also possible to access via to the oscillating to an anti-state of the initial state and decaying to the same final state. Okay, I will show you a bit more. Okay, the direct CP violation in the V system has been very well measured. This is for the V2K pi system. For instance, this was measured by Belle. So you can see here the difference in this. This is for two different decay modes, and that there is a difference in this asymmetry from the particles and antiparticles decaying. Okay, this is well known, and it has been also observed by LHC experiment. For the time-dependent CP asymmetry that I am showing here, in this case, what we are doing, it is just to check if for one state, so the one anti-V0 going to a final state, a CP against a final state, and the V0 going to the same one. For instance, in one of the examples, one of the golden modes for this kind of measurement for the CP asymmetry, it is that the V0 meson decaying to a Gibbs-ion and a K short. Okay, so then you have this kind of decays. Okay, what do we have to do? It is to measure and to determine very well which is the flavor of our initial state in all the cases, but to know how many V0s and how many anti-V0s we have at the beginning. We know we have to be able to reconstruct the final state in a good way, and also we have to measure, because this is always dependent on the time. We are this asymmetry we are always studying depending on the time. We have to have a very good time resolution. Okay, and this has been measured by the B factories. You can see it very clearly here, and how this asymmetry looks like. Okay, this is for the B zero tags and for the anti-B zero tags. And if we measure this CP asymmetry, and the formula you can approximate to something like that, and it is given. So if you consider okay, that this is about zero in the standard model, what you have it is that you are sensitive to the sin to beta, which is this constraint here in the CKM matrix, in the CKM unitary triangle. Okay, this sin to beta that I'm sure that Karim will talk a lot about it. It is given by this CP asymmetry constraint. Okay, and okay, I'm not explaining too much. This is the formula, including the experimental effects. You can check it with a specific decay modes. At the end, you can measure, and this is the measure of the LHC. So in total, the measurement of this CP asymmetry, it has been done, and this angle, this sin of 2 beta, has been measured by different experiments and by using the different channels. You can see that the precision it is really very high, and at present the beta angle, this beta angle in the CKM matrix framework, it is very well measured. Okay, and in fact, if you look at now at all the CKM picture, and you can do it here from this CKM feature in this web page, you can see all the observables that they are there. You can see that everything it is fitting quite well, and that you have, if you are just looking at the pool of the different observables, all of them, they are quite compatible with the standard model prediction. So that means that the new physics, it has to be, the effects here, they have to be very, very thin, and that at present the main effects are observed all in rare decays, And I think that's all what I wanted to say. I think it's time, right?
Yes, it's come to the end of the hour. But did you have anything else that you wanted to conclude, or is, I think this figure is also how Yuval concluded his talks, because it's such a marvelous thing.
Yeah, it is a marvelous thing, or it is a pity thing. It depends on how you see it. What it is clear, it is that the CKM picture, it is now it is very well measured, let's say. So it is really, really good pressure, and the precision that we have reached, it is amazing, and yeah, it is compatible with what we have as the Flavour model in our standard model. So I think rare decays now are much more encouraging for detecting new physics.
Yes.
This
okay, so
my feeling.
The last chance to ask any questions to Arantza.
Okay, you can always send me questions by mail in any case, or if you want.
So there's a question from Lijuan. What is the definition of N-mix and N-unmix when you were showing the mixing measurements?
The N-mix and N-unmix mean the ones that they are oscillating and the ones that they are not oscillating. I don't know if I have it.
Yeah, so that it was here.
Yeah, it is here. It is just the one. I don't know if I have. Yeah, it is the number that they have been oscillating and that they have not been oscillating. That they are coming in yeah.
So, yeah, so the flavor tag is used to define this. Yeah. Because you could, there's so-called self-tagging on decay, and then you use the flavor tagging to see how they were produced.
Exactly.
And you can see if it's mixed or unmixed. I imagine, again, both Karim and Dighe will talk more about flavor tagging.
Yeah, sure. I think he's going to talk a lot about it, I hope. And it will have, I think, will have also the picture where you have how it is produced, a meson, how it is decay, how you measure, I mean, how you tag it at the at the one that this plot that you were talking yesterday, I think, where you can see the time difference and all. I think he will talk very clear about it.
Okay. So there's nothing else here in the chat right now. So thank you so much for spending the time.
Thank you very much. Thank you very much. I hope that you enjoy, and then I wish you very good lectures next one.
And well, we hope to see you in India again before too long. Huh? Now things are getting back to normal.
Okay, so take care. Okay.
Thank you very much, Arantza. Bye-bye.
Thank you very much. Ciao, bye.
Bye, Arantza.